So I think last week we continued looking at the unity load method, and I think we focused more on the how to calculate um, displacement for beams and for beams. So one key. Um, so let me just put here recap. Okay, what is happening? Okay, so recap. Yeah, so we looked at deflections. All right, okay, which was to look at displacement of vertical displacement. Um, yeah. For beams, largely it is vertical displacement. All right, because of the fact that the axial um, axial displacement are largely assumed to be what's the name, negligible. All right, so and then we did mention that if you want to find the displacement, then it's the moment due to the virtual load, which is typically is going to be the unit load divided by the moment in a real beam or the moment from the external loads, and then then that should divided by the EI, which is the flexural rigidity. All right. So basically, this is how to calculate the the displacement at a point on a beam. And then for the rotations, theta is equal to again. Here, with this moment is gotten from placing a unit moment at the point where we want to find the rotation, right? So these two are slightly different, all right? So let's take a note of that. Okay, so this were the um, these were the equations that we were using, all right? So I think largely we should be able to, um, when given a problem of this nature, we should be able to use the information available to calculate any deflections whatsoever. Okay. So let's look at something entirely different this morning. Uh, we will be looking at some other new topic. I mean, it is a pretty short topic. It's not anything uh, long. Let me just get myself something quickly. So today I want us to look at a new topic. So that is going to be influence lines four trusses. All right. Um, in CENG 0155. You guys looked at the influence lines for beams, right? I think largely it was statically determinate beams. All right. Okay. Um, so we will build on it. We'll build on that set of information and then come up with the ILDs for sorry, what's happening to my internet? Just a second. Uh, see. All right. So I mean, just some small recap. I'll spend the next 30 minutes or so just to do a recap of what's the name? What the ILDs are all about. Okay, I think I did mention that I do have a video that is talks about like ILDs for beams. In case someone claims to have interest in it, I can post that to you guys. Maybe as a refresher, but then largely I will spend my time on trusses and just some few minutes to explain like the basic concept using beams, so we can move on to the trusses. All right. So let's look at it this way. What we have been doing so far, or what we've been looking at so far, has been uh, that if you have a beam or some frame system or some truss system, you usually have some load on it. All right. So what happens is that the the loads are stationary. Uh, so stationary loads, which means that the loads are not moving, right? And then based on this stationary or this fixed loads, we determine. So based on this, we determine shear force. All right, and this is the shear force on the entire structure, and then bending moment. Sorry, bending moment for the entire structure. All right, so we have loads fixed at a point or fixed across maybe it could be the entire span or some point. But then the key thing that the loads are fixed, right? So even if it's a UDL or it's a point load, the loads are always fixed in location and also in time. They don't change in time, they're always where they are. And then based on that, we determine functions. These functions can be reactions, they can be shear force, it can be bending moment. We'll find them along the entire length of the beam. All right. So these are typically when we draw them, therefore, normally for the entire span, right? Normally, yeah. The entire span or the entire length of the structure. Okay. So normally if you have this to be your beam, let's say that here we have 3, 4, and 3 meters. Your bending moment diagram or okay, let me start with the shear force. Your shear force diagram. Just trying to figure out why I have different pen thicknesses. Okay. So your shear force diagram, oops, will look like this. So I think it will take a shape like that. All right. So that if maybe this is four, let me put some unit. If this is 4 kilonewtons per meter, then it means that your reactions VA and VB will be the same anyways. So this is A and B, they will be the same. So each one will be 8 kilonewtons, right? You can check this up yourself, but each one will be 8 kilonewtons, okay? So the load is fixed in space, and then we find its behavior or its effect along the entire span. So in this case, span AB, all right? In the same way also, you can take this information here and then draw the bending moment diagram, right? The bending moment diagram, you have something like this. Okay, then you have this being a curve. Okay. So this is shear force diagram and bending moment diagram. All right. So these are basically what we have been looking at. Okay. But truth be told, there are some loads um like some loads on structures where these loads are not fixed in space or in time as well, right? So when that happens, so there are some loads on structures uh, that uh, are live or moving. All right. For example, if you take a bridge, all right, eh, um, most of us should have seen the Adome Bridge around the Akosamo area, or some bridge system. There are some small bridge systems on the Accra Tema motorway, and even some of our major highways do have some bit of overpass and underpass. All right, so they are technically bridges in a way, but this is that we give them special names. All right, and these bridges have loads on them, but the loads are not chairs and tables, or but they are typically vehicles, right? So on bridges, you would realize that our loads are vehicles or vehicular traffic, and you would realize that the loads tend to move. All right. So if you have, let's say, a bridge, so you have this bridge, okay, so the same bridge, all right. At some point in time, you could have the load over here. Maybe that's the car. Maybe let's say some CRV or some kind of brand. So when the time t is equal to maybe 1 second, for example, you have the car at this location. Let me call this location K. Then you come back in a few seconds, let's say 2 seconds, and the car has moved to a new location called L. So now it's the same car, the same everything about the car, but it has changed location. Then you come to another instant in time, let's say 3 seconds, and then now the car has moved to a new location called maybe M. All right. So it's the same car, but it keeps changing its position with respect to time. Okay. What this means is that when at t is equal to 1 second, you have your VA. So we call this one VA1. At time t equals 2 seconds, you have, let's say, VA2. At time t equals 3 seconds, you have VA3. Because the positions of the car keeps changing with respect to time, it means that at these three different times, your VA would also change. All right. So, unlike in the case whereby you have stationary loads, or what you can also call maybe dead loads, because they are not moving, not dead loads as in the types of loads, but the fact that the loads are pretty much stagnated. Uh, you can see the difference that in this case, because the loads are stationary, it doesn't matter what time we look at, the load's position does not change. All right. But in the case of moving loads, with respect to time, the load's position will change. And then as the load's position will change, it means that certain functions like reactions, deflections, shear force, and bending moment will also change with respect to the new position of the the car or this moving vehicle. All right. Uh, so yes, some examples of such structures are bridges, but we also have more examples. So examples of structures that experience moving loads or that have moving loads. Okay. So one example is a rail. All right. So um, and this is any place that has a rail system, again crossing some bridge system or whatever, it can also add up to, I mean, what you term as moving loads. Um, then if you have a building that has an industrial or maybe an industrial building with cranes, okay, you go into certain industries and they have these large overhead cranes which are part of the building to move items maybe across the floor, all right? And these tend to, because the cranes move up, I mean, left and right, and then so north and south, east and west kind of movement. They are termed as moving loads, and we design the columns and the beams that they sit on to receive such moving loads. All right. Some also can have where we have conveyors. All right. So where we have conveyor belts, which also move items from one point to the other, they pretty much experience moving loads. All right. Um, sorry. So let's see. Okay. So if you have the case whereby the loads are moving, it means that it is difficult to determine things like shear force for the entire beam. All right. Because then what it means is that you have to determine the shear force for the entire beam at every instant in time, right? So do you use every minute to decide whether that becomes your interval for the time change, or will you go for every second, or will you go for every hour, or is it going to be every millisecond, every microsecond, right? It becomes near impossible to be able to draw the shear force diagram for the entire spans, right? So if you take, let's say, when t is equal to um, I mean, 1 second, you have your, for example, let's say shear force diagram. So your shear force diagram will look at this, will look something like that. Okay, let me just, this becomes your shear force diagram. I think I have overdrawn it. This becomes a shear force diagram, assuming this is largely a wrong shear force diagram. Let me do the right thing. Okay. So let me just create space below. Okay. So I think I have so your shear force diagram. Okay. So it looks this way. Let me okay, great. Now I think I have enough space to draw. So this could be a shear force diagram for t is equal to 1 second. Then when you come here, your shear force diagram, depending on the load system, there'll be some slight differences. So this is perfect. Then when you come here, this is how your shear force diagram. This should be this one should be a bit bigger. Great. All right. So your shear force diagram is also changing, right? So now what do you do? If you have a moving load, and we came out with the idea that okay, if you have the case whereby you have live loads or moving loads, the best approach would be that you would rather look at the effects of this moving load at a point on the entire structure. All right. So you are not looking at the effect of the moving load on the entire span of the structure, but rather you are looking at the effect of the moving load at a point on the structure. So, for example, as feedback. Okay, so this should be fine. All right. So if you look at what they will focus on that, okay, let me call a point here, maybe point let me call this point P. So there's a point here, point P, and point P will remain point P in space. All right. So now what we are looking at, okay, let's look at the effect of this load on point B. So if the load is at 1 second, what will be its effects at point P? When the load is at 2 seconds, what will be its effect at point P? When the load is at 3 seconds, what will be its effect at point P? And then based on that, we'll draw some diagram which will so let me just draw a funny shape. So we draw a diagram, and this diagram would be the effect, all right, of the car on point P. All right, which means that as the car approaches point P, uh, the effect of the car on point P will start increasing. All right. So that effect can also be termed as its influence. So the influence of the car, all right, on point P. All right. You would also come to see that uh, let's say for a bridge, right? I mean, most of us have used the Accra Tema motorway several times. You would realize that we don't have one type of vehicle on the roadway, right? It could be a truck, it could be a very small car like a Vitz, it could be a saloon car, a Corolla, a Civic, or it could be a CRV, it could be a Nissan Patrol, it could be a pickup truck, it could even be an articulated truck. So you would see that, or even motorbikes, for example, right? So you could see that even on the same bridge, there are different sizes of vehicles. All right. So what do you do? Are you going to draw the effects of all these different vehicles, its effect on a certain point on the bridge? That would take forever, right? So what do we do? Instead of using the loads of the vehicles or some other moving loads, we take a unit load. So 1 kilonewton load, and then we look at its effects on different points or different sections on the beam, or let's say on the bridge. Then we draw diagrams. Then based on these diagrams, if later we have the actual size or the actual loads coming from the let's say the cars or the vehicles in this case, then we can use that information with our diagram to determine the actual influence based on the size of the vehicle. All right. So let's look at a few things, and maybe that would explain the concept to us. All right. So we define. So now let's define influence lines. Since I've mentioned it. Okay. So influence lines are they are pretty much lines which represent lines that represent okay, uh, a variation um, of a function. All right. At a specific point. All right. So that's a key word, specific point. Um, so in a member or members as a concentrated. Okay. So load. So typically we use a unit load. All right. Uh, moves across the member. Okay. So the functions, now we can look at some examples of the functions. Now we can look at, we have reactions as one of the functions, uh, shear force, bending moment, and then even deflections. All right. So for now, we'll look at these three. All right. We'll do the deflections next semester, which we'll do that more into what we are looking at. Sorry, we are looking at fixed, sorry, statically indeterminate members, right? Like beams with so many supports here and there, right? Okay. So in in with regards to what's the name? What you guys did. So let's just do a recap of beams. Let's look at beams. Okay. So for example, if you have a beam, all right, so this is your beam, nicely drawn, and then you have a unit load, 1 kilonewton, right? This here is the entire length of the beam, but because the load is moving, we don't know at what points we have this load, all right? And we want to find, for example, the ILD. So I'll be sort of saying the influence line diagram, I'll just say ILD. So find the ILD for, let's say, a reaction at A. Okay. So what this simply means is that as the load is moving from point A to point B, what will be the reaction at A? All right. So in simple terms, let me see if I could. Okay, let me just go this way. All right. So let's say, if for example, let's make L 10 meters, for example, for just simplicity's sake, right? So we can have a case whereby, oops. So let's say the same beam, all right? Right. So I'm just trying to explain the concept. We could have the load, the 1 kilonewton load right here. Okay. So if it's right at A, your VA or your RA is 1 kilonewton, and then your VB is 0. Okay. So this is, let's say, time t equals 0, right? That's just when the car or the vehicle has just hit the 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 start of the bridge. Now let's look at another instance. So the same everything, right? Then this time around, our load is some 2 meters away. All right. Now, if this is still 1 kilonewton, your VA is 0.8 kilonewtons, then your VB is 0.2 kilonewtons. All right. Let's just go again. 4 meters. Oops. So 4 meters. Now your load has moved some distance, let's say 5 meters. All right, let's just use 5 meters. Okay. So at this point, you see that your VA is 0.5, your VB is also 0.5. Okay. Now again, let's move the goalpost. Now our load has now moved. So let's say this is 2 meters now. So this whole thing is 8 meters. So now your VA is 0.2 kilonewtons, and then uh, your VB is 0.8 kilonewtons. Okay. Again, let's say the load has moved. Now your load is right at the top of B. So your VB is 1 kilonewtons, and then your VA is 0. Okay. So you can see that again, if you have any questions, you could just ask me through the chat. Send it to the one. I think I can see a question somewhere. Yeah, so you're saying that the more the load gets to the point, the more the influence at that point. Yeah, yeah. Typically, yes, yes, yeah. So as the load is approaching a particular point of interest to you, its influence on that point is higher. All right, and we'll see that very shortly. Um, so we can see that. So now what we are looking at the reaction at A, right? So with the reaction at A, it means that its influence or the largest influence would be when the load is at A. And we can see that clearly over here. Let me see. Uh, all right. So we can see that over here, when the load is at A, it's 1 kilonewtons. If we move to 2 meters, it's 0.8. If we move to 1 kilonewton, VA is 0.5. If we move to 8 meters away from A, VA is 0.2. And finally, when the load is at B, VA is 0. So I can decide, okay, you know what? Let me plot it. Let me plot this whole thing. So I have 0, I have 2 meters, and I have 5. I think I have 8 meters, and I have 10 meters. All right. When the load is at 0 meters, VA is 1 kilonewton. When the load moves to 2 meters, VA is now 0.8. Let me move this one up a little. So this is 1 kilonewton. When the load moves to 2 meters, VA is 0.8, as we can see. So 0.8. When the load moves to 5 meters, VA is 0.5. okay? And when the load um when the load moves to 8 meters, VA is 0.2, and when the load moves to 10 meters, VA is what? 0. So I can look at this and then just draw a line. Oops, my line is so bad. I'll try to draw. Oops, okay, it's fine. I'll just draw a straight line. I just put a point in there. Let me just put this point here. So this is 0.5, this is 0.2, and this is 0. All right. So this diagram here becomes the influence line diagram for reaction at A. All right. So what this simply means is that we are looking at the different positions of the 1 kilonewton load and how it affects VA, or RA. All right. And it means that when the load is at A, its highest effect on the reaction at A will be felt when the load is at point A. As the load moves from A to B, its influence begins to reduce to the point where at B, the influence goes to 0. So that's what you guys, I think, did in your first year basic structures class. Until this was be like a recap, all right? So you can find reaction at A. You can also find the ILD for reaction at B, which then becomes the opposite in this case, all right? So here again, if the load is at B, VB is 0. If the load moves to 2 meters, VB 0.2, 5 meters, VB 0.5, 8 meters, VB 0.8, then at 10 meters, VB is 1 kilonewton. So you would realize that your diagram will just be the opposite. So this is going to be, so this will be the ILD for reaction at B. All right. So we can do this for reactions. We can do this for shear forces. We can also do this for bending moment diagram. All right. So you can rewrite this whole thing here using variables. Variables are, they make things easier because then you can apply the same equations to, as long as the same structure, you can use that equation throughout. Okay. So going back, once it's 6:30, I think I should move on to something else. All right. So we know that if you have this here and that over here, you have a load on it, and this is 1 kilonewton, and this distance here is x, and the whole length here is L. You can find VA. You can also find V, right? So, of course, VA plus VB equals 1 kilonewton. Okay. That can be established if you're summing vertical forces, right? So let's say this is A and this is B. Summation of moment at A equals 0. All right, so what do you get? You get VB times L minus 1 times X equals 0. All right, so let's make VB the subject. VB here is equal to X over L. So if VB is X over L, this implies that VA will be equal to 1 minus X over L. Or some will say L minus X over L. It's the same thing, all right? So this equation can be used. I mean, so this helps us. The reason why we prefer to write some of these, whether I share many moments or reactions in terms of X is because of the fact that your load is a moving load. All right, so if you write equations in terms of X, then you can replace X by the different points. For example, if you want to find the ILD for reactions at A for intervals of 2 meters. Then your X becomes intervals of 2 meters, 0, 2, 4, 8, 10, up to whatever span length that you have. Okay. This equation is valid for this particular beam configuration. All right. If you have a different beam configuration, the equations might change slightly. Okay. Where's my mouse? Okay. All right. So this can be used for shear, for reaction, for bending moment as well. Again, as I've mentioned, I have a video on it. So if you seem interested on that, at least maybe to act as a refresher, to recap whatever you did in first year, you can arrange and I can have that sent to you. All right. But in the meantime, I'm going to jump straight to my trusses, I think, so that I don't spend too much time on this. All right. So for trusses, the idea of the influence lines for trusses is slightly, there are just slight differences, but they pretty much work the same as I've just discussed. All right. So, because if there's going to be any questions in the exams, then those questions will be on the trusses. All right. So normally we call trusses pin jointed frames. And the reason for such beautiful name is that we assume that the members are strictly axial members, right? They transfer loads through axial behavior, which means that they are not designed to resist moment. So we also ensure that in our analysis, the loads are positioned in such a way that they do not cause moments in the members, all right, or even at the joints. The Again, you don't have a perfect system like in reality where like they are strictly pin jointed, which means that the joint acts as hinges where they only resist translational loads, vertical and horizontal. You will still have some moments in there, but because we are assuming that the moments are negligible, design them as such. All right. So let's look at the typical. So we have trusses for roofs. So trusses, we can find some for roofs, typically for bridges. These are the common areas where truss systems are used. I think in your basic structures, you looked at different types of truss, the highway, HOWE, the Warren truss. We had a different type of truss that you guys looked at in your first year, first semester course. So how they really go there. Um, so let's take, for example, a bridge truss. All right. They normally would experience, or bridge trusses normally would experience moving loads, right? Roof trusses hardly experience moving loads, right? Hardly, except maybe when you have a crane in there. But largely you might put a brace on beams, right? And not on the roof, the roof beams per se, all right? So normally bridges are the best examples to explain the truss system. Okay. So let's say we have this truss. I'm just going to explain. Okay, so this is a typical truss. Another one that we can have. Okay, so this could also be another truss system, right? And the difference between this truss system has to do with where the load is positioned, where the moving load is positioned. Right. So normally, if you have a bridge, like let's say one, this is two. For one, normally your you have your the deck, right, where the cars move at the bottom. So the deck, um, so in a way, so let me explain the parts of the truss, which I think we should already be aware. This is the top chord, okay, and then we have the bottom chord. Okay. Then, so if this is the side view, so these are the side view of the truss. When you come to the plan view where the deck is, it's made of a series of beams going, oops, let me change the color. Yeah, made of a series of beams going along the length of so these are the beams. Okay. Then they are intercrossed with what we call stringers. Okay. Then when you have this mesh-like system of normally bridges are made up of steel, and then when you have this system in place, then you would cast either concrete over it to act as the deck or as a platform on which the vehicles will move. Right? So it could be concrete, reinforced concrete for most cases, or sometimes it could even be a steel plate. But naturally, would prefer to use concrete, or when we have the steel plates, we place a thin layer of asphalt on top of the steel plate so that it is it provides traction for the vehicles. I mean the tires of the vehicles. All right. So if you've ever been to Accra Circle, you'll see that they have this little overhead, which we call I think it's called Dubai, right? Yeah, Ghana, Dubai. That side of town where we have this overhead uh, road system. So that one was largely constructed using steel material, and the deck is also steel. So they place some thin layer of asphalt on it to mimic a typical roadway, right? So in this case, you have your vehicles, um, so your vehicles moving at the bottom. Okay. Then in case two, again, in case two, this is your top chord. So wait, it just so this becomes your top chord, and then this is your bottom chord. Okay. The only difference is that the decking is at the top. So in that case, your vehicles are moving. So here, vehicles move on the top chord. Okay. And in this case, vehicles move on the bottom chord. Okay. I think I need a new. Sorry, my PC is just going up crazy on me right now. I get my pen to work. This is not good. It stops for a second. See, just give me a second. Let me figure out what's happening.
Okay. All right. So sorry about that. I have to change laptop. The other one just decided to go off on me. All right. Okay. So back to discussing the what's the name? The types of process that we can have in terms of like where the loads would be moving on. So they can either move on the so the loads move on the okay, I have to change all my colors. The loads can either move on the okay, is it rather the pen that is a problem? Okay. Uh, this is becoming an interesting morning. Now that is interesting. Okay. All right. So the vehicles that move on the bottom chord. All right, and let's some move on the on the top chord. And so when it comes to trusses, some of the functions that we look at. Um, so there are three that we typically look at. We look at the reactions as support. Okay. So reactions as support, as we have been looking at in beams. They also look at the forces in the members. All right. And these are typically axial forces, right? We don't do bending, we don't do shear, we only do axial forces. Then we look at deflections as well. But again, we will focus on these two. All right. Okay. So let's look at how typically a truss system is understood to work. All right. So let's say we have so let's say that we have what's the name? some truss. Uh, this- so we have this truss. Let me just see if I can draw. All right. So we have this. So um, we have A. Let's say B, D, D, E, F, G, and H. Let me add one more. Great. Okay. And let's say the supports at A. So these are the supports, all right? And the entire length, the lengths are equal. Just so each one is 6 meters, 6 meters, 6 meters, and the height is also 6 meters. All right. And let's say we have a unit load. So a unit load um, moves from A to E. All right. So that's supposed to be the bottom chord. Okay. Let's take note of that. So means that our system is moving at the bottom chord. All right. And let's say, for example, we are being asked to find the influence line diagram, ILD, for reaction at A, or maybe A and E. All right. So what this means is that we place, all right, so just like with the beams, you have cases whereby you can look at the position of the load. All right. So at one point in time, you have your load positioned at A, right? So if your load is positioned at A, what will be the reactions VA? You have unknown reactions here. You have unknown, so VE, VA, and then HA. All right. So what would be these reactions? All right. Uh, because it's a unit load, a vertical unit load, it means that your horizontal reaction HA almost all the time will be zero. All right, because of the fact that you only have vertical loads on the structure. So now, if you look at A, okay, where our X at A, oops, at A where the X is equal to 0, we know that VA plus VE is equal to 1 kilonewton. All right. And then if you sum moments about A to be equal to 0, let me just expand this a little bit, to be equal to 0, uh, it means that it becomes VE times 24 equals 0, because both VA and then the 1 kilonewton act at the same point A. So that their moment arm will be 0. So this implies that your our VA will be equal to 1 and our VE will be equal to 0. Okay. Now let's take this load, this 1 kilonewton load. Okay, as I've drawn it, let me see if I can delete it. Okay, let's take it and now place it somewhere around B. So now your load is now here. Okay, so let's say at B, let me divide this so that we see the differences. So at B, where your X is now 6 meters. So again, it's always VA plus VE. In this case, it's 1 kilonewton. So here, if we take moments about A to be equal to 0, if you sum moments about A to be equal to 0, you have 1 times 6 to be equal to VE times 24. All right. So this will give us a VE. We get a VE of 1 over 4 because 6 over 24 is 1 over 4. Then you get a VA of oops, a VA of 3 over 4. All right. Then let's move the load again. So we come back here and move the load. Yes. Let me just redraw this. So we have this. Let me just redraw. So now we move the load to C. All right. So now C is a 1 kilonewton load at C. So if that is the case at C, what will be your reactions at A and E? That's the general idea, right? So at C, it means that, so at C, X is equal to 12 meters, all right? So it means that, again, your VA plus VE will be equal to 1 kilonewton. It's random 10 max, okay. And then if you take moments, again, if you start moments about A, to be equal to 0, it becomes 1 times 12 equals VE times 24. You'll see that a pattern is being developed, right? So here VA would be half, and then VE would also be half, all right? So we can apply this to the other sections, so D and E, all right? So if we do at um, D, where X is equal to 18 meters, you will see that our VA will be equal to 1 over 4, and our VE will be equal to 3 over 4. Then if you do the last one at E, where X is equal to 24, you will soon realize that our VA goes to 0 and our VE becomes 1 kilonewton. Okay. So I can write a nice table from here on. Let's put a nice table together, right? So this is our X, and these are VA, and these are VE. So when X is 0, 6, 12, 18, and 24. So when X is 0, V is 1, V is 0, 3 over 4, 1 over 4, half, which is same as 2 over 4, half. Then it becomes 1 over 4 over here, and then 3 over 4, and then 0 and 1. Right. So you can use this information to draw your influence line diagram for, let's say, for example, a reaction at A or for a reaction at E. So for the reaction at A, all right. So we have the abscissa of the X. So we have 0, 6, 12, 18, 24. Let me take away the rest. Okay, great. So since we know the values for A, so when X is 0, A is 1. When X is 0, A is 1. When X is 6, A reduces, keep reducing, and it goes to 0. So here, this diagram with a straight line over here becomes the influence line diagram for reactions at A. So ILD for reaction at A. The same way we can also take the points for B there. So these are the ordinates, the 0, the 1/4, 1.5, and these are the ordinates for that point. We can also similarly use that information and then end up with a diagram looking this way. So this becomes the ILD. So note the points as we go from 0, 6, 12, 18 to 24. And this becomes your ILD. Here's 1. This is what? 3/4 over here, 1/2. And then we have 1/4. All right. So this is the ILD for reaction at B. Okay. And this is how we calculate reactions. All right. Take a note. Hey, sorry, did I say BE? Reaction at E, not because let's go support at B. Please take a note. For this particular class system, our supports are at A and E. Take notes. The thrust can change. It can be in a different configuration. And so the positions of the support can also change. All right. It's not always at the end. So if you go here, you can see a pattern being developed right there. Okay. Especially with these equations, you see a pattern being developed. Maybe if I add one more for the 18, okay, then one more for the 24, you see a pattern being developed. Okay. So X, all right, so I can maybe just do this one, maybe add here one, um, or maybe let me just rewrite this guy here. So let's say 1 times 0 is equal to VE times 24. So I'm just rewriting that to help me to see the pattern being developed. So in effect, this equation here is simply 1 times X equal to what? VE times L. All right. So 1 times X equals to VE times L. And what this simply means is that my VE is equal to what? X over L. All right. So if you're able to formulate this equation, you don't need to do this at A, at B, at C, at D kind of calculations. They take forever. Especially if you have a very long what's the name? A very long class to deal with, they take forever. And you wouldn't want to go through that process. Formulate an equation for that particular function makes it easier to do your calculations. All right. So V is equal to X over L. It means that when X is 0, VE goes to 0. When X is 6 meters, in this case, RVE becomes what? 6 over 24, which is 1/4. When X is 12 meters, VE is 12 over 24. And now that becomes what? Half or 2/4. So that's how we are able to write those equations, all right, without much stress. Okay. So if V is equal to X over L, and then VA plus VE is equal to 1, then it means that VA is equal to 1 minus X over L. All right. And that's how we are able to get the data set for the VA as well. All right. So this is in its simplest form, how to calculate for reactions at what's the name? At different supports. All right. Now let's look at the forces in the members. All right. Because that's what all this is about, trying to find forces in the members. All right. So the first part here Also look at one of my screen is not responding, which is quite strange. I don't know why. Okay. All right, so let's look at the forces in members. Okay. So at this point, your understanding of classes plays a critical role, especially using the method of sections. Okay. Method of sections to calculate your deflections at different points on the truss. But again, let's look at some example to use that to explain the concepts, and then that will help us to appreciate better what we are looking at. Um, so now let's look at to the same truss as above. Um, let me just copy that in. See if I can place it somewhere. Copy, paste. Where is it pasting? Okay. Move to the right for me. Okay, so now let's look at this example. Okay. So here, the same structure, all right. But here, instead of finding reactions, we want to know the forces in the members. All right. So let's take three members of interest to work. Member GH, member GH, member BG, and member BC. Okay. So let's say, I think I'll do for two of them. So find, oh, sorry, more or less draw ILG for forces in members. We have GH, we have BC, and then we have B. So for these members, we want to draw uh, the forces. And here it's easier to go with the method of sections, right? I didn't explain last week or the week before that when we are looking at trusses, you are, depending on what you are looking at, you can use either the method of joints, which is the most common, or the method of sections. All right. And the method of sections is used where you are looking at just some few members of the support. I mean, of the some few members of the trust and not the entire trust system. All right. So to do that, we cut a section. Let's call that section KK. We'll just cut a straight line. Call that section KK. All right. So if you cut that section, you have a left-hand side and also, so here's your left-hand side. You also have a right-hand side. Okay. So the section to the left of K is the left-hand side, and the section to the right of K is the right-hand side. Okay. So now let's go through the first principles, and then maybe that will help us to appreciate what is happening. Then we can look at how to use equations to also solve these types of questions. Okay. But let's look at a case where x is at 0. Okay. So if x is at 0, or if we have the load where at x equals 0, what do we do? So now our load is somewhere here. Okay, acting right at A, or let's say at A also. Oops. So at A, where X is 0, what would be the forces in the members? All right. So we know that when we have a load at A, let me take this guys off so that I can have space. When the load is at A, our VA is equal to 1, and our VB is equal to 0. That sorry, VE, that we have already established, right, from previous calculations. Okay. So our VA is 1 kilonewton, our VE is 0. That we already know. So now let's look at the sections. I would spend a bit more time here to explain this concept to us. So if you cut a section at KK, you have two parts. We have uh, this part right here. So let's say, let me call this one FGH. This is FBG, then FBC. Okay. You still have your load here, your 1 kilonewton load over here. You also have your VA also over here. So this is the left-hand side. Okay. I can do the same thing on the right-hand side, just so that we see what goes into these calculations. Okay, so we have here, so this is what we have from this end. Oops. It's supposed to be straight. Okay, so here's our FGH, this is our FBG, our FBC. Okay, so these are, so this again, let me just, this looks funny. Oops, go back, redraw. All right, so this are right-hand side. Okay, so at our right-hand side, we only have VE. When V is 0, VA is 1. Right. So you can decide to use either the right-hand side or the left-hand side to solve this problem. It's entirely up to you. Usually, I have found out or from experience or even from books, you will be told that it's easier to use the side that does not have the unit load. Okay. So at this point in time, our unit load is on the left-hand side. So it's easier using the right-hand side to do your calculations to find the forces in the members. FGH, FBG, and then FBC. All right. So let's look at so let's say I'm using the right-hand side. Okay. It doesn't matter. I mean, it will still be the same thing anyway. So we need to know these angles, theta. Okay. We need to know what theta will be. Okay, so we need to find theta. We can easily find theta. All right. Um, theta is 45 degrees. All right, because I have this here, I have that here, I have so this is from the F, so this is G and this is H, and this is what am I correct? Oh, so that the opposite. Here's H and here is G, and this is B. So the angle here is theta. This length here is 6 meters. This height here is also 6 meters. So that makes theta 45 degrees. All right. Because tan theta is equal to 6/6. So theta is equal to tan inverse of 1, and that'll give us 45. All right. So let's take a look. So the angle here is 45. It makes our calculations easier. All right. So if we are dealing with the right-hand side only, then we take moment about a point. All right. Um, Normally, you have two options. If you are to extrapolate, sorry, if you are to extrapolate the, the system here, the right-hand side, this is more or less like the part that we cut away so we don't see it. All right. So here will be our H, I believe. This will be our B, I believe. So this is our G, and this is our C. All right. So we can take moment about either H or B. All right. It's entirely up to us. But it's also best to look at which point that when you take moment about, your equation becomes easier to work with. Right. And I do believe that when we sum moment about B, it makes our calculations easier for us. All right. Um, Before that, we can even look at summation of forces. Right. It's good to look at that. So summation of forces, let's say vertical forces equals 0. What this means that VE minus, this is FBG, sorry, I think the G went out somewhere. So if we take this load, FGH and FBC are horizontal loads, all right? They are strictly horizontal loads. So they will not have any vertical component. But FBG, since FBG, so this is our FBG. So our FBG is in this direction. It means that it would have a vertical and a horizontal component. So this is our FBG. Okay. So the vertical component of FVG, it becomes FBG sine theta. Since our angle is adjacent to the horizontal, so it becomes sine theta. And then the horizontal component becomes FBG cos theta. This much I think we should be able to decipher. All right. So if you are summing vertical forces, you will see that VE is going upwards, so I can make that one positive. Then the vertical component of FBG is a downward force, so it becomes negative. So it becomes VE minus FBG sine theta equals 0. So here, what this implies is that my FBG will be equal to VE over sine theta. Okay. But at this point, V is 0. So if V is 0, then our FB is also what? 0. Okay. So now I found FBG. So FBG is 0 when your load X is 0, or when your load is at X equals 0, or when your load is at A. When your load is at A, your reaction at VE is 0, and that will give us an FBG of also 0. Okay. And if FBG is 0, so now we know FBG. Let's find FGH or FBC. So if it's some moment at B, which I mentioned earlier to make things easier for us, here is where your clockwise and anti-clockwise case come in. You need to pay particular attention at how the forces can cause rotations about the point and which direction these rotations are in. All right. So since we take it moment about B, it's like we are holding B as the pivot and then we rotate the truss based on what kind of loads that we have. Okay. So with respect to VE, the moment between B and E is 18. There are three of the six, so it's 18 meters. All right. And this will cause a counterclockwise rotation about me. All right. And if you take FGH, FGH will also cause a counterclockwise rotation about B. So that makes both VE and FGH positive in terms of moment. All right. And then the moment is this height here. That'll be 6 meters. And this will give us 0. All right. FBG and FBC are passing through the point B. So their moment goes to 0. Let me see if there's any question anyway. No, we don't assume. The idea of the influence line diagram is that there's always a unit load active. Sorry, I'm answering somebody's question. They want to know if we should always assume that the load on the truss is a unit load and it's one, and also that the distance on the deck are the same. Because you are drawing an influence line diagram, you draw it always with a unit load. So that part is fine. You always draw with a unit load, but the distance on the deck can vary. It depends on how the deck was designed. Normally, trusses are designed to have the same space and normally the same spacing throughout, and for convenience of construction and all of that. And also makes the design fairly straightforward. But it's not always the case that you have the spacing between the vertical chords being the same. All right, and it's not always the case. I've seen bridges that have uh, different spacing. All right, so just take a note of that. In this case, yes, but sometimes it can vary. Okay. Um, all right, so going back, so here we can tell that our FGH will be equal to 0. Okay, now let's sum horizontal forces. Let me do that on this side. Uh, Summation of horizontal forces equals 0. So here our FGH plus FBC equals 0. All right. So since FGH is 0, our FBC is also 0. All right. So when the load is at one, um, oops, when the load is at A, the forces in the members FGH, FBG, FBC equals 0. All right. So now let's move to the second case, um, where our load is now at B, where X is equal to 6 meters. All right. And now we mentioned that what VA is 3/4, and then VE is 1/4. We found that already. All right. So what is going to happen is that to make things easier for me, I'm just going to copy everything I have from before. I think I have overcopied. I'll delete a few items. I need these guys here. Let me redraw this. Okay, so this is fine. So it means that our load is no longer here. Sorry, it's no longer our load is no longer this. So our load is now as B. So this is let me draw it right down this way. Fine if it's nice if it's drawn this way. So this is your A, this is your B. All right. So now the load is at B. Since the load is now has now moved to B, our VA, oops, our VA is what? 3/4, and our HVE, sorry, is 1/4. Again, it's easier using the side that does not have the unit load. All right. Always easier going with that. So again, you see that patterns are being formed. Um, if you sum vertical forces, in this case, summation of vertical forces equals 0. So you have again VE minus FBG sine theta equals 0. Right. Nothing is changing. I said that is the same equation I'll end up using anyways. Um, okay, so I just copied everything from 0 to 6 meters. All right. So here at 6 meters, we have, I've been like to slow down, so let me slow down. All right. So we have a load acting at B, or the unit load has moved from A to B. All right. So since it has moved from A to B, we still using the method of section to determine the forces in the members. All right. The whole idea of what we are doing is that at every instant in time, the load has moved. All right. So maybe at time t equals 0, the load was at A. At another time, the car has moved to B. At another time, it has also moved to C, and then D, and then E. All right. So if it's at A, what will be the forces in these members? BC, BG, and then GH, which we have solved and previously. Now the load has moved to B. All right. So since it's moved to B, what again will be the forces in the members? BC, BG, and then GH. So it's like we keep solving for the same thing based on the different positions of the unit load. Okay. And the best method to use is the method of sections. All right. So you cut your beam whereby you can have uh, at most 3 unknowns. All right. Please take notes. If you have more than 3 unknowns in the members, it is difficult to do your analysis or your calculations in this case. Okay. So let's see. So it's the same equation I'm going to use. Here I'm summing vertical forces, right? So I'm using the right hand side, okay, to solve it. It's easier that way. So vertical forces, V is upward. The vertical component of FBG will be acting downward. I've already explained that previously. So this becomes my equation, VE minus FBG sine theta equals 0, right? So from here, our VE will be equal to sorry, no, we're looking for F. So FBG will be equal to VE over sine theta when it goes to divide. All right. So VE is 1/4 divided by sine 45. Okay. So if we do that calculation, uh, you will get 0.354. Okay. Now let's take moments about B. So again, everything I wrote earlier, I'm bringing the same thing. Okay, the load is at B. Why is it not included as part of the vertical forces? And I mentioned that because you are using the method of sections, you cut your beam, your truss into two parts, right? So we have the left hand side over here. So this whole thing is the left hand side, and then we have the right hand side. Okay, you can use one of them to determine the forces in the beam. All right, and since we cut the beam, okay, not beam, since we cut the truss somewhere in between, as you can see here, we cut the truss somewhere in between like this. So it means that our load has now moved from A and is now here. All right, so our load is now here. Okay, so you can see that it is still on the left hand side and not on the right hand side. All right, so you can either use the left hand side to solve for the problem or use the right hand side. One of them, not all of them, one of them. And as I mentioned earlier, it's easier to use the side that does not have the unit's load at that point. All right. So again, coming here, because our unit's load is at B, because it's at B, we have not so on the right hand side, we will still not see our unit's load. All right. So it's easier to use the right hand side for our calculations. Okay. We'll see what happens in the next instance, in the next case shortly. Okay. So here, if you some moment at B, it becomes VE times 18 plus FBG times 6 equals 0. FGH. Okay. If the answer is not adequate or not okay for you, you can still send another message. Okay, so I know that is good or not. So here, our our FGH will be equal to negative VE times 18 over 6. All right. And this is the same as negative, our VE is 1 over 4. So negative 1 over 4 times 18 over 6. All right. And if we do it that way, um, this will give us an answer of 0 minus 0.75. Okay. So this becomes our FGH. Now we can sum horizontal forces. So here FGH plus FBC equals 0. All right. So it means that our FBC will be equal to negative FGH. All right. So this should give us, hopefully I'm correct. I haven't done anything. Oops, sorry. I made a very big mistake. Sorry. Okay, let me go back over here. Because I was wondering why I wasn't getting the right answer. Okay, sorry. So let me come back all the way here. When you are summing horizontal forces, there are three of them and not just two. There's the FGH, there's a horizontal component of FBG, and then the horizontal FBC. So please, this equation here actually would be FGH plus FBC plus FBG cos theta, okay, equals 0, right? But here still FBC still 0 because everything is 0. All right, please take note. So let me go back here and correct this unpardonable mistake. So it becomes FGH plus FBC plus FBG cos theta equals 0. Please, they all move in the same direction. Okay, so just take note of it. So here our FBC will be equal to minus FGH and minus FBG cos theta. All right. So this is your equation. Your FGH was minus 0.75. So you have that already there. Then minus FBG, you got FB to be what? 0.354 cos 45. Yeah. So this will give us 0.5. Okay. So our FBC, so we have our FBC, we have our FGH, we also have our FBG. Right. So in this case, you'll see that when the load moves to 6 meters, these are your calculations. All right. Now let's look at when the load X, I know it's wrong. X is at, sorry, let's say at C, where X is now at 12 meters. All right. So I see where X is at 12 meters, our VA is half and our VE is also half. Okay. So I'll just paste whatever I copied earlier. And the same thing over here. Okay. So now our load is no longer at B, but now our load has now moved to what? Point C. Okay, oops, sorry. Struggling with the screen today. Um, okay, so our load is no longer at this is A, this is B. Our load has now moved to C. So now our load is here. Okay, our load is now at the right hand side. This is your 1 kilonewton load. All right. And as I mentioned, it's easier to use the side without the unit load. All right. So in this case, I'll prefer to use the left-hand side for my calculation and not the right-hand side. Previously, I'll use it my right-hand side because it was easier. I mean, you don't have to deal with extra loads on the structure. But since now the load has moved to the right-hand side, it is easier to now use your left-hand side for the calculations. Easier. It doesn't mean it's impossible to use the other side. All right. So here, this angle theta, oops, have this angle theta, which is the same as the one we had earlier because it's the same system. So here our VA is half. Our VA is half. All right. So these are the only loads that we have on the left-hand side. Do we consider the direction of the arrow for which we take the reactions for the horizontal and vertical forces? Um, so let me get the question right. So what I understand by your question means that, like, by convention, normally when you are finding reactions, even in year one, you would usually point your reactions to be acting upwards. All right, because normally lows tend to act downwards. All right, so by definition, your loads are always acting upwards, like normally, because for influence lines, you are draw influence lines are usually drawn for a unit load which is acting downward. All right. So because you have your unit load acting downward, especially on the bridge system, it means that your reactions would act upwards. All right. And once your reactions act upwards, if you get a positive value, then it means that the direction in which you chose your reaction in is the same direction that the answer is in, pretty much. But if you get a negative answer for your reaction, which you see sometimes, then it simply means that the answer is in the opposite direction to the direction you assumed your reactions to be in, and that's all there is to it. Okay. Normally, when you're dealing with forces in members, you usually assume that they are moving away from the joint, that the forces in the members are in tension, and that's the reason why if you look at my two diagrams, whether it's left hand side or right hand side, they're all moving away from their respective joints. All right. If you get a positive value, it means that your forces in the axial or your axial forces in the members are in tension. If you get a negative answer, it simply means they're in compression. And that's all there is to it. Okay. So let's look at C, where it's at 12 meters, and we'll see what to do with it. So at 12 meters, we are looking at the left-hand side. It's easier to work with the left-hand side. All right. So now let's sum. So let's do vertical forces. Summation of vertical forces equals 0. So here VA plus the vertical component of FBG is going upwards, right? So here when you come, this is your FBG. So this is your FBG, and you have a component going upwards and one going this direction. This is FBG sine theta. Please take note of the position of the angle theta. Okay, so what about the horizontal forces? So I did mention earlier that when it comes to the reactions, so going all the way back, sorry, struggling to expand. Okay, so going all the way back, we mentioned that because you only have vertical loads, I mean your unit load is a vertical load, right? And since you only have a vertical external load on the system, the horizontal reactions most likely will be zero, right? Because HA equals zero. There's no other horizontal external load to uh, uh, um, 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 equate the external horizontal reaction to it. So that would be zero, all right? So for ILDs, we are only looking at the vertical unit load across the length of the track. All right, okay. So let's get here. So here becomes VA plus FBG sine theta equals zero. All right. So it means that our FBG will be equal to minus VA over sine theta. Okay, so this will be equal to minus half over sine 45. Okay. And this should give us minus 0.707. So we found the first force in the member. Now let's sum moment about B. Okay, summation of moments about B equals 0. So let's so about B, which one is easier? It's up to us here. So if I'm to extrapolate this a little bit, here's our G, and then this is oops. So our B will be somewhere here. So this is our B. All right. So we're taking moments about B. We would get which one is easier? sorry, that's it. That was B. B is right here. So B is right in front of us. So this is B. We're taking moments about this point B. So that it means that it becomes VA times 6 moments about B, and VA and plus FG or FGH. All right, they go in the same direction in terms of their rotations. They are all clockwise. So they are all in the same direction. So all of this equals to 0. All right. So our FGH here will be equal to our FGH will be equal to minus VA times 6 over 6. Right. So pretty much it's equal to minus VA. All right, which is equal to minus half. So that's our FGH. Now let's do uh, summation of maybe horizontal forces. Let me write it down here so that it doesn't confuse us. We're looking at something entirely different. So summation of horizontal forces equals 0. So again, we sum, so it becomes VGH plus um, VBG cos theta plus FBC equals 0. So what are we looking for? FBC. So here our FBC will be equal to minus FGH, then minus FBG cos theta. All right, so this will be equal to minus our FGH is minus half, so minus half. Then minus FBG is also minus 0.707, so cos 45. And all of this should give us 1. So our FBC will be equal to 1. So here our load has moved to 6 meters, sorry, 12 meters. So again, you say patterns being developed as you go along, and we will use the patterns. So now at D, where X is what? 18 meters. Okay. So now where X is 18 meters, you'll see that the same idea is being used. So now at 18 meters, our VA is now 1 over 4, and our VE is 3 over 4. Okay. So let me just go here. So our at 18 meters, that's at D. So this is D. Our 1 kilonewton load is no longer at C, but now it has moved to D. So this is 1 kilonewton, right? So VE is 3 over 4, and VA is 1 over 4. This is supposed to be half. All right. Okay. So this is what you have. Again, it's easier dealing with the left-hand side. All right. So with some vertical forces again, so summation of vertical forces equals 0. So again, I'm dealing with the left-hand side and not the right-hand side. So it becomes VA plus FBG sin theta equals 0. So again, you see that here V is what? What do I always keep writing V? So FBG will be equal to minus VA over sin theta. Okay, so that'll be minus. So here our V is what? Minus 1/4 over sin 45. And that'll give us minus 0.354. And then if we sum moments about B equals to 0, same idea, nothing has changed. So it becomes VA times 6 plus FGH times 6 again equals 0. And then here we know that our FGH is equal to minus VA. So it becomes minus 1/4. Okay. Then if you sum up vertical forces, we already have that equation over here. So I can just pull it out. I can see that nothing really changes. It's just the same equations being used with different values. That's pretty much what is happening, and nothing else changes over here. So here our FGH is minus 1/4. So see, I'm just changing the equation, just changing values, nothing. And once we do that, um, our FBC, I believe will be 0.5. Yes, will be 0.5. All right. So we have all of that. Now the last bit to look at is when we have our load at E, where X is equal to 24 meters, right? At that point, our VA is 0 and our VE is 3, sorry, it's 1. Okay, it's 1 kilonewtons. Okay, so once this happens, what do we do? So again, the same uh, structure as before. So I can literally copy everything I have over here. Just copy everything on low battery. Copy everything that I have, and then did I copy? I don't think so. I can paste the same. Okay, it's taking a bit to copy. I think it's gonna take some seconds to paste. Okay, great. So nothing is actually changing. Let me just change the values, and you see that the same thing is being used over and over. So now I have my 1 kilonewton load at E. So now my load is at E. So I have it right here, 1 kilonewton units load at E. So at E, we get 1. At VA, we get 0. Okay. Oops. So if it's a VA, we get 0. And it means that here is 0. This will give me 0. And VA is also 0. So this gives me 0. And if all of these are 0, it becomes 0 over here, and then 0. So this is 0, 0, and 0. This is 0. All right. So we can see that at when the load moves to E, all our loads are 0, or all our forces in the members are 0. Okay. So you can take all of this, draw a nice table just to um, explain what is happening. And then when we draw this nice table, we should end up with something um, looking like that. I've been drawing halfway, halfway. It's interesting. So we should end up with something uh, in this form. All right. So I've just rewritten the all the assets that we had in this table nicely. All right. So um, Oh, the laptop went off. There's no sound. So is the sound back? Hello, can anyone answer? Oh, okay. So we are good, right? Okay, great. So I hope you didn't miss anything, or hopefully. Yeah. All right. So this is what we have. Um, oh no, the table, I just copied the table. So the table has to do with our answers, all right, for the different forces in the members here. So that if the load is at 0 meters, FBG. So if you go back all the way up here, when the load was at A, our A, our FBG, where's FBG, FBG, FBC, and then the FGH was 0. All right. Then when the load moved to 6 meters, FBG was 0.354, FGH was minus 0.75, and then FBC was 0.5. All right. So I just took all of that data and put it into this table. All right. So that it's easier for us to look at the table and then draw from the table. So in this case, if I have this length, so this is the bottom chord. So I have so this is 0, 6, 12, 18, and 24. So this is the bottom chord of our bridge. So now, if I'm looking at FBG, for example, okay, so at 0 meters, the value of FBG is 0. At 6 meters, the value of FBG, it jumps to 0.354. At 12 meters, our FBG has come all the way to negative 0.707. And then at D, it moves closer to minus 0.354. And at E, it goes back to 0. All right. So you just take a rule, draw straight lines between the points, then you get a diagram like this. Let me just move this points. Okay. So this diagram becomes an influence line diagram for forces in member BG. Okay. So we can draw the same thing for member GH. All right. So we take and put GH somewhere here. So for member GH, it also starts at 0. Then it goes to uh, negative 0.75 somewhere here. It comes to 0.5 and then 0.25 and then 0 again. So it also has this shape. All right. So this is 0, minus 0.75, minus 0.5, minus 0.25, and then 0. So this is for ILD, for forces in member GH. Okay. Now let's draw the last one for member BC. And for BC, it starts at 0, it moves to 0.5, then it goes to 1, and it comes to 0.5, then 1, then 0 again. So it looks like this. Okay. So this is 1, 0.5, 0.5. So this is for ILD, for forces in member FBC. Okay, so that's pretty much what order we've done is to give us this information. Now, if you look at it carefully, I'm just going to take us through something the next 5 minutes or so. If you look at it, where is this thing? Okay. We established this set of equations, all right? That VE is x over L, and VA is minus or 1 minus x over L. Great. So what this means is that coming back here, assuming we want to put together a general equation for whatever we've been looking at, we have already established. So I'll write which color? With green. Green is nicer. We know that VA is 1 minus x over L, and then VE is equal to x over L. Okay. So I can take these sets of equations as I have and then rewrite them to suit my equations because that is easier to work with. All right. So um, when we are using the right-hand side for our calculations, all right, we saw that our FBG was equal to VE over sine theta. All right. We saw that happening a lot. All right. So this is the same as what? Assuming VE is x over L. So it becomes x over L sine theta. All right. Or this becomes x over L times sine theta. It's the same thing. All right. So that if your L is equal to our L is 24 meters, that's the length of the entire span, then this becomes um, x over 24 sine theta. Let's see if this makes sense to us. Okay, so let's say so this is valid when you have now all equations are valid between sets of ranges. We've seen that several times. We were using the right-hand side when our load moved from A to B. All right. Once our load moved to C, we began using the left-hand side, which means that this equation is only valid. So it's valid. Maybe different color should help. Valid for A or between A and B, which means that when X is from 0 to what would that give us? To 6 meters. Okay, so 6 meters. So that's only when this equation is valid. Okay. So consider when X is 0, our FBG is also 0. When X is 6 meters, our FBG will be equal to 6 over 24 sine. Was that negative somewhere? Yeah. So if you do these calculations, you would get, you can always cross-check with your calculator. You will get 0.354. So it becomes 6 divided by 24 times 45, and you get 0.354, which is what we had using the first principle approach, right? So this equation works great. Now let's write another equation for FGH. We mentioned that VE, so it was VE times 18 plus FGH times 6. 6 is the height, and this was equal to 0. So which meant that our FGH was equal to minus VE times 18 over 6. So this becomes minus x. Our L is 24. So x over 24 into bracket 18 over 6. So we can simplify this here, and then we'll get what? So 18 divided by 24 times 6. And this one will give us um, minus x over 8. So this becomes your equation. Again, this equation is also valid for just this case. So for the right hand side. Okay. So if x is 6, it becomes minus 6 over 8. And minus 6 over 8, it's 0.75. Okay, or minus 0.75. In the same way, you can also write an equation for the last bit, which is the FBC. So our FBC, we got it to be what? Minus FGH, looks too small, minus FBG cos theta. So it means that this is equal to minus, our FGH is what? So minus into brackets, minus x over 8, then minus into brackets, x over 24 sine theta cos theta. All right. Well, I'm guessing uh, so then this becomes the equation for that. And then let me then you can put in the theta is 45 in this case, and then you have another equation. All right. So again, this equation is valid for between 0 and 6. All right. The reason why we are going through these steps is that you usually don't want to go through this first principle stuff, right? Because it takes forever to get it done, and you don't have uh, uh, the luxury of time to get all of these done. So using or creating an equation makes the computation process easier. Now, for the other parts, we're looking at the left-hand side. Okay. So with the left-hand side, where our x moves from 12 meters to 24 meters. Right, so from C towards E. All right. So it means that again, we can also formulate the equation for the left-hand side. And then so our FBG will be equal to we got minus VA over sine theta, and our VA is x over L. Oh, sorry, 1 minus x over L. Sorry. So this becomes 1 minus x over L divided by sine theta. Okay. You can expand it, and then it becomes easier. And expand this whole thing, it becomes easier. All right. Then our FGH, which one is it? Okay, then our FGH will be equal to minus VE. So it becomes minus into brackets 1 minus x over L. You can again expand, and when you expand, this simply becomes x over L minus 1. Yeah, I know it's time. Let me just complete it, and then it should be okay. Then our FBC is minus FGH minus FBG cos theta. All right. So that this becomes minus into brackets minus. So this is a quite an interesting equation to write. So let me do the brackets, big brackets. Minus minus 1 minus x over L divided by sine theta. This is one bracket. Then Hopefully I'm writing the right things. Okay, let me put it this way. So the FG8 is simply minus x over L minus 1. Okay, that one is straightforward. Then minus bigger brackets. This is also x over L minus 1 times cos theta divided by sine theta. Okay, so this is a much more simple approach. All right. So there are a few things to take notes from whatever we've been looking at today is that um, for thrusters, we need to, it's easier if we determine the forces or the reactions first. No, this equation only works for this particular thrust. For different thrusts, the equation will vary slightly. All right, but the equation works for the particular thrust. Equations are typically specific, or like structural minima specific. All right, okay. So I'll solve a few more examples and then add it to this, and then you can have all of that. Let's go through your notes and we go through it. If you have any questions and then you think we should meet next week, please let me know. All right, so that we could maybe add a bit more material to the skeleton. Okay. All right, let's see ourselves again another time. Enjoy the rest of your weekend.